Watch this thread. It's thinner than a single hair off your head. And right now, it is dragging a fully loaded coach bus. Engine off, brakes off. 54 adults sitting inside without snapping. Not stretching, not fraying, not snapping. Try that with a steel cable the same thickness, and it tears apart before the bus moves a single inch. This isn't a movie prop or a computer render. This happened, on camera, in 2026. And almost nobody outside the material science world has heard about it yet. Here's the number that should stop you. 8 times stronger than steel. 75% lighter. And unlike most insane material breakthroughs that quietly die in a lab and never get mentioned again, this one isn't sitting in a research paper collecting dust. It's being mass-produced right now, on a real factory floor, shipping to real customers. By the end of this video, you'll understand exactly how a strand thinner than your hair can outpull steel, why it took China 2 full decades to pull this off, and why Japan and the United States, the 2 countries that have quietly controlled this industry for 50 years, just got a serious wake-up call. But before we go there, I need 30 seconds from you. If you've ever watched one of these China manufacturing breakdowns and thought, why did nobody tell me this was happening? That's exactly what this channel exists for. Hit subscribe right now before you get pulled into this story and forget. And once you finish this video, I want one word from you in the comments. Just one word. Real or hype. By the end, you'll have a genuinely informed opinion on which side of that line this falls on, and I want to know exactly where you land. Let's get into it. Before we get to the breakthrough itself, you need to understand why this problem was so hard in the first place, because it isn't really a chemistry problem. It's an engineering problem, and it's one of the most expensive problems in the entire modern world. Strength-to-weight ratio decides almost everything about how we build things. Every plane that flies, every rocket that launches, every electric car on the road, they're all fighting the same war. The stronger you make something, the heavier it usually gets. And every extra kilogram costs real money, real fuel, and real range. Steel has been the default answer to that problem for about 150 years, because it's cheap, it's predictable, and it's everywhere. But steel has a hard ceiling. Standard structural steel tops out around 400 to 500 megapascals of tensile strength. Push past that, and you're adding exotic alloys, more cost, and more weight, and the returns start shrinking fast. Carbon fiber was supposed to be the answer to that ceiling decades ago. The idea is simple on paper. Carbon atoms, arranged in a nearly perfect chain, can be incredibly strong while weighing almost nothing. The problem was never the idea. The problem was actually building it, strong enough, thin enough, and cheap enough, at a scale that industries could actually use. Think about it like trying to braid a rope out of individually unbreakable threads. Every single thread might be incredible on its own. But the moment you try to bundle millions of them together into something you can actually build a wing or a car panel out of, the connections between them become the weak point. For decades, engineers could make small, expensive laboratory-sized batches of very strong carbon fiber. What they couldn't do reliably was scale that same quality up to industrial volume without the strength quietly falling apart somewhere in the process. That's been one of materials science's most stubborn unsolved problems for an entire generation. Until now. On March 11, 2026, at the JEC World Composites Trade Show in Paris, which is basically the biggest stage that exists in the entire advanced materials industry, a Chinese state-owned company called China National Building Material Group unveiled something nobody else in the world had managed to do. They didn't just design a stronger carbon fiber. They mass-produced it. In the carbon fiber world, there's something called the T grade, and it functions like a scoreboard. It's how the entire industry measures how advanced a country's materials manufacturing actually is. China had already climbed from T300 all the way up to T1000 over the past several years, one careful step at a time. T1200 is the new top of that ladder, and as of this year, China became the first country on Earth to produce it at real industrial volume, not just inside a laboratory. Now, let's talk about the actual numbers, because this is the part that makes engineers sit up and pay attention. Tensile strength, over 8 gigapascals. That's roughly 8,000 megapascals, compared to standard structural steel's 400 to 500. Density, about 1/4 of steel's, which is exactly where that 75% lighter number comes from. And a single strand of this material is about 10 times thinner than a human hair. To prove this wasn't just a marketing claim dressed up for a trade show audience, researchers twisted 120,000 of these hair-thin filaments together into a single rope less than 2 millimeters thick. That rope was strong enough to tow a fully loaded coach bus, 54 adults inside, without snapping. That's not a polished lab demo number picked to sound impressive. That's a stunt built specifically so nobody could accuse them of exaggerating the claim. Now here's the part. Most coverage of this story skips entirely, and it's honestly the most interesting piece of the whole thing. Making T1200 grade fiber isn't really about discovering some brand new magic material. Carbon fiber itself has existed for decades already. What this actually required was controlling a brutal manufacturing process with near-perfect precision every single time across thousands of tons of material. The process works in two main stages. Stage 1 is called pre-oxidation. The raw precursor fibers get heated to somewhere between 200 and 300 degrees Celsius. This stabilizes the molecular structure before the real transformation even begins. Stage 2 is carbonization, and this is where it gets intense. Those same fibers then get blasted with heat up to 2,000 degrees Celsius inside a tightly controlled environment. At that kind of temperature, almost everything except pure carbon atoms burns away completely, leaving behind an almost pure carbon chain, aligned in a near-perfect structure at the atomic level. Here's why that matters so much. If you get the temperature control wrong by even a small margin, across a batch containing thousands of individual filaments, the strength of the final fiber drops fast, and the whole batch can be effectively useless. Holding that kind of precision consistently, at scale, for 100 tons a year, is the real 20-year achievement here. It isn't the underlying chemistry. It's the manufacturing discipline behind it. The lead researcher on this project, Chen Chufeng, put it pretty simply. Mass production is exactly what turns a material like this from an expensive laboratory rarity into something entire industries can actually build real products with. And that distinction matters more than it sounds like it should. There's a huge difference between a research team proving something works once, under perfect conditions, with a hand-picked sample, and a factory proving it can produce the same quality thousands of times in a row, batch after batch, with real workers, real equipment, and real deadlines. Plenty of exciting materials have died quietly in that exact gap between the lab and the factory floor. This one didn't. Now, this isn't a one-company story, and it's genuinely important that you know that, because it completely changes how you should think about this whole race. A separate Chinese company called Zhongfu Shenying released its own version of this material around the same period, marketed under the name SYT80, with almost identical specs. Roughly 8,000 megapascals of strength, and a density around 1.79 grams per cubic centimeter. When that specific announcement hit the markets, the company's stock jumped by its full daily trading limit in a single session. But here's the honest part that most videos covering this story leave out completely. China isn't winning this race alone, and it definitely isn't winning it easily. Japan's Toray Industries is still the global leader by total volume, producing somewhere around 29,100 tons a year. That's more than 250 times China's current output. And Toray has also already developed its own 8 gigapascal T1200 fiber of its own. Mitsubishi Chemical is planning to double its high-end production capacity by 2027. South Korea's Hyosung is targeting 24,000 tons of capacity by 2028. And here in the United States, a company called Hexcel remains the primary supplier for American military programs specifically. So what actually changed here isn't that China suddenly leapfrogged everyone else overnight. What changed is that for the first time, China proved it can genuinely compete at the very top tier of this specific technology, instead of just being known for the cheap, low-grade end of the carbon fiber market like it used to be. And that shift matters strategically too, not just commercially. Advanced carbon fiber isn't just a consumer material. It's on export control lists in more than one country, precisely because it shows up in fighter jets, missiles, and satellites, alongside everyday things like bicycles and tennis rackets. A country that can produce its own top-tier supply doesn't have to worry about another country cutting it off during a crisis. That's a very different kind of value than just saving weight on a car door. So where does this material actually end up in your life? Because this isn't just an aerospace story sitting far away from anything you'll ever touch. Think about hydrogen fuel tanks first. Lighter, stronger tanks mean genuinely safer, high-pressure storage for hydrogen-powered vehicles, which is a real bottleneck holding that entire industry back right now. Think about electric vehicles next. Every single kilogram you save on a car's body panels or its battery casing turns directly into extra driving range on the same battery. Think about drones and flying taxis. China's entire so-called low-altitude economy, all those ambitious plans for urban air mobility, depend on materials exactly like this one existing at scale. Think about medical devices and prosthetics, where lighter and stronger components make a real physical difference for the actual patients who have to carry or wear them every single day. And of course, think about aerospace and defense, the obvious application, where strength-to-weight ratio has always meant the difference between a program that genuinely works and one that simply doesn't get off the ground. None of this happens overnight, and I want to be honest with you about that. But this is exactly the kind of unglamorous, boring-sounding manufacturing breakthrough that quietly reshapes entire industries 5 to 10 years down the line. The same way early advances in lithium batteries or LED lighting didn't feel remotely dramatic back in year one either. Nobody watching those early battery factories in the 1990s thought they were watching the birth of the smartphone or the electric car. It just looked like a slightly better battery for a camcorder. This tends to be how the biggest material shifts actually happen. Quietly, industry by industry, until one day, the thing that used to be exotic and expensive is just sitting inside a product you bought without ever thinking twice about it. Now I want to slow down here and be completely straight with you, because a lot of videos covering this exact topic round the story up to make it sound bigger than it currently is. First, the volume is still genuinely small. 100 tons a year sounds impressive right up until you compare it directly to Toray's 29,100 tons. China has absolutely proven that it can make T1200 fiber at real industrial scale. It has not yet proven it can make it at Toray's scale. Those are two very different achievements. Second, the actual cost isn't public yet. Ultra-high-strength carbon fiber has always carried a steep price premium over standard grades, and nobody has published exactly what T1200 costs per kilogram at this point. That single number is going to decide how fast this technology actually spreads beyond aerospace and defense into more everyday products people like you and I might actually buy. Third, you've got two separate companies making two very similar claims at almost the same time. CNBM's T1200 and Zhongfu Shenying's SYT80 have strikingly similar specifications, but come from two different organizations entirely. That's either genuine parallel innovation happening inside China's broader carbon fiber industry, which does happen, or it's overlapping marketing built around similar underlying research. And honestly, right now, there simply isn't enough independent, outside verification available to say with full confidence which one it actually is. And fourth, there's no long-term field data yet. Steel earned the trust it has today through 150 years of real bridges, real ships, and real buildings, including plenty of genuine failures along the way that taught engineers hard lessons. This new material has months of headlines behind it right now, not decades of real-world stress testing out in the field. None of that erases what's genuinely been achieved here. It just means the honest headline isn't quite China beats the world. It's closer to China just became a real, credible player at the very top of a market it used to be almost completely locked out of. Step back for a second, and this whole story fits a pattern you've probably already noticed if you follow Chinese manufacturing stories closely. Solar panels, electric vehicle batteries, shipbuilding, and now, advanced composite materials. The playbook stays remarkably consistent every single time. Enter a market relatively late. Spend nearly 2 decades on unglamorous, patient process engineering that almost nobody outside the industry finds exciting. And then arrive with genuine production volume right at the exact moment the rest of the world is still debating whether any of this is even possible. Carbon fiber has been a Japanese and American stronghold for generations at this point. That is no longer fully true anymore, even if it isn't fully false either. Whether China can actually scale this from 100 tons a year all the way up toward Toray's 29,000 tons is the real question that decides whether this whole story becomes a small footnote in a much bigger book, or the next entire industry that China ends up quietly leading a decade from now. So here's what I want you to sit with. If a material this strong ends up inside the phone in your hand, or the plane you're flying on 5 years from now, would you even know it was there? Most people never do. The biggest material shifts in history almost always happen completely invisibly to the ordinary people using them every single day, without anyone ever announcing it to them directly. And that's exactly the problem. Nobody announces it. Nobody puts it on the news. The only people who find out early are the people who are actually paying attention right now to channels that are digging through this stuff before it becomes mainstream. If you made it this far, you're already one of those people, and that's not an accident. So don't let it stop here. Hit subscribe right now, genuinely, before you scroll to the next video and forget this ever happened. Because this exact story, China quietly closing a gap nobody thought it could close, is going to keep repeating, industry after industry, and I am covering every single one of them the moment they happen. And remember what I asked you at the start. One word. Real or hype? Drop it in the comments right now, before you even finish reading the sentence. Real, if you think China actually scales this into a genuine threat to Toray and the West. Hype, if you think this stays a headline that never quite catches up to itself. I am reading every single comment on this video, and I will be replying to as many of you as I possibly can, because I want to know exactly where this audience stands. So type it now. Real or hype? And I'll see you in the next one.